is Isro-Vssc Technical Assistant Electrical Engineering previous year question paper with a detailed solution. Exam held in 2017. First question. A single phase transmission line of impedance 0 plus j 0.8 ohm supplies a resistive load of 500 ampere at 300 volt. At the sending end, the power factor is answer is option D 0.6 lagging. Given impedance is j 0.8 ohm, current is 500 ampere and voltage is 300 volt. We know Vs equal to Vr plus Izs, where Vs is the sending voltage, Vr is the receiving voltage and Zs is the line impedance. Therefore, Vs equal to 300 plus 500 into j 0.8, that is 300 plus j 400. Magnitude equal to root of 300 square plus 400. We get magnitude as 500 and phase phi equal to tan inverse of 400 by 300. We get 53.13 degree. Therefore, Vs equal to 500 angle 53.13 degree. Power factor cos phi equal to cos 53.13, which is equal to 0.6. Question number 2. A single phase load of 100 kilo volt ampere is delivered at 2000 volt over a transmission line having R equal to 1.4 ohm and X equal to 0.8 ohm. When the power factor of the load is unity, the voltage at the sending end is answer is option D 2070.4 volt. In a single phase transmission line, Vs equal to Vr plus IL angle phi Z, where Vs is the sending end voltage, Vr is the receiving end voltage, IL is the current flowing through the transmission line, Z is the impedance of line and phi is the phase angle. Given SL equal to 100 kilovolt ampere, Vr equal to 2000 volt, power factor equal to 1, therefore phase angle phi equal to 0. Z equal to R plus Jx, which is equal to 1.4 plus j 0.8. Magnitude of IL equal to 100 into 10 raised to 3 divided by 2000. We get 50 ampere. Therefore, IL angle phi equal to 50 angle 0 degree. Then sending end voltage Vs equal to 2000 plus 50 angle 0 degree into 1.4 plus j 0.8, which is equal to 2000 plus 50 into cos 0 degree plus sin 0 degree into 1.4 plus j 0.8, which is equal to 2000 plus 50 into 1 plus 0, that is cos 0 is 1 and sin 0 is 0, into 1.4 plus j 0.8. Then we get 2000 plus 0.5 into 1.4 plus j into 50 into 0.8. After simplification, we get 2070 plus j40. Magnitude of Vs equal to root of 2070 square plus 40 square. We get answer as 2070.4 volt. Phase phi equal to tan inverse of 40 by 2070. We get 1.10 degree. Third question. The corona loss on a particular system at 50 Hz is 1 kilowatt per kilometer per phase. The corona loss at 60 Hz in the same system would be answer is option D 1.13 kilowatt per kilometer per phase. Corona loss PL equal to 241 into 10 raised to minus 5 into F plus 25 divided by delta into root of R by D into V0 minus Vc whole square kilowatt per kilometer. This is the equation number 1, where F is the supply frequency in Hertz, R is the radius of conductor, D is the distance between two adjacent conductors, V0 is the operating voltage in kilovolt, V is the critical disruptive voltage in kilovolt. Delta is the air density correction factor. Given F1 equal to 50 Hz, F2 equal to 60 Hz, corona loss PL1 equal to 1 kilowatt per kilometer per phase. From equation 1, we can analyze corona loss PL directly proportional to F plus 25. Therefore, PL1 of 50 Hz divided by PL2 of 60 equal to F1 plus 25 divided by F2 plus 25. Substituting the values of F1 and F2 we get, and also PL1 value, we get the value of PL2 of, that is PL of 60 ohm equal to 1.13 kilowatt per kilometer per phase. Question number 4. If voltage is increased n times, taking into consideration of constant efficiency of a transmission line, the size of conductor will be area of cross section. Answer is option C, decreases to 1 by n square times that of original. If we want to transmit the same number of watts, the current will be 1 by n when the voltage is increased by n. For the same amount of loss, the new diameter of the wire will be 1 by n. The amount of copper will be 1 by n square. So when voltage is increased by n times, then for the same efficiency, size of conductor is reduced to 1 by n square that of the original. Question number 5. A shunt reactor of 100 megawatt ampere reactance is operated at 98% of its rated voltage and 96% of its rated frequency. Its capacity is, answer is option C, 100.04 MVAR. Reactance Q equal to V square by XL, which is equal to V square by 2 pi FL. Q2 by Q1 equal to V2 by V1 whole square into F1 by F2. Given Q1 equal to 100 MVAR, V2 equal to 0.98 V1 and F2 equal to 0.96 F1. Therefore, Q2 equal to 100 MVAR into 0.98 V1 divided by V1 whole square into F1 divided by 0.96 F1. After solving, we get Q2 equal to 100.042 MVAR. 6. Precautions are essential for ensuring that the secondary of a current transformer is not open circuited when the primary circuit is carrying current. This is due to, answer is option A, dangerously high voltage might develop across secondary. The secondary side of a current transformer is always kept short circuited in order to avoid core saturation and high voltage induction, so that the current transformer can be used to measure high values of currents. Current transformer works on the principle of shorted secondary. It means that the burden on the system ZB is equal to 0. Thus, the current transformer produces a current in its secondary which is proportional to the current in its primary. Most important precaution in use of a current transformer is that in no case should it be in open circuited even accidentally. As the primary current is independent of the secondary current, all of it acts as magnetizing current when the secondary is opened. This results in deep saturation of the core, which cannot be returned to its normal state, and so the current transformer is no longer usable. Again, due to large flux in the core, the flux linkage of secondary winding will be large, which in turn will produce a large voltage across the secondary terminals of current transformer. This large voltage across the secondary terminals will be very dangerous and will lead to the insulation failure, and there is a good chance that the person who is opening the current transformer secondary while the primary is energized will get a fatal shock. Question number 7. In the waveform shown, the RMS value of the voltage is, answer is option D, 100 volt. RMS value is based on the heating effect of waveforms. The value at which the heat dissipated in AC circuit is the same as the heat dissipated in DC circuit is called RMS value provided. Both the AC and DC circuits have equal value of resistance and are operated at the same time. RMS value or effective value of an alternating quantity Vrms equal to root of 1 by t integral 0 to t v square of t dt, where t is the time period. For a rectangular wave, the RMS value is equal to average value. RMS value is also equal to peak value. For given waveform, RMS value is 100 volt. The other waveforms, maximum value, average value, RMS value, form factor and peak factor. For sinusoidal wave, the maximum value is Am and the average value is 2 Am by pi. RMS value equal to Am by root 2. Form factor equal to RMS value divided by average value. Substituting the RMS value and average value terms, we get form factor as 1.11. Peak factor equal to maximum value divided by RMS value. We get answer as root 2. For square wave, maximum value, average value and RMS value are Am. Therefore, form factor and peak factor is 1. For triangular wave, maximum value is Am, average value is Am by 2, RMS value is Am by root 3, form factor equal to 2 by root 3 and peak factor equal to root 3. For half wave rectified wave, maximum value is Am, average value is Am by pi, RMS value is Am by 2 and form factor is pi by 2 and peak factor is 2. Question number 8. In a domestic electric installation, the maximum load permitted in a 60 ampere power circuit is, answer is option B, 3 kilowatt. In a domestic electric installation, the maximum load permitted in a 60 ampere power circuit is 3 kilowatt. For determination of load of an installation, the following ratings are: fluorescent lamp 40 watt, incandescent lamp or fan or socket outlet 60 watt, power socket 100 watt, exhaust fan as per capacity of exhaust. The number of subcircuits are decided as per number points to be wired and total load to be connected to the supply system. In one light and fan subcircuit, the maximum load that can be connected is 800 watt. Question number 9. A dielectric of relative permittivity epsilon R is introduced in an air capacitor of capacitance C0. Its capacitance will become, answer is option B, epsilon R C0. Capacitance of a parallel plate is C equal to epsilon A divided by D, where epsilon equal to epsilon naught into epsilon R, where epsilon naught is the permittivity of free space or absolute permittivity, which is equal to 8.85 into 10 raised to minus 12 farad per meter. Epsilon R is the relative permittivity of dielectric medium. D is the distance between plates. A is the area of plates. For air capacitor, epsilon R equal to 1. Therefore, C0 equal to epsilon naught into A divided by D. When a dielectric of relative permittivity epsilon R is introduced in an air capacitor of capacitance C0, then C0 dash equal to epsilon naught into epsilon R into A by D. We know that C0 equal to epsilon naught A by D. Therefore, C0 dash equal to C0 into epsilon R. 10. The forbidden energy gap of germanium is, answer is option C, 0.7 electron volt. Semiconductor, band gap at 0 Kelvin and band gap at 300 Kelvin. For silicon, band gap is 1.21 electron volt and at 300 Kelvin band gap is 1.1 electron volt. For germanium, band gap is 0.785 electron volt and in 300 Kelvin band gap is 0.72 electron volt. Gallium arsenide, band gap at 0 Kelvin is 1.52 electron volt and band gap at 300 Kelvin is 1.47 electron volt. By heart these values. Question number 11. In a single phase diode bridge rectifier, the load resistance is 50 ohm and source voltage is 200 sin omega t volt. Omega equal to 100 pi radian per second. The power dissipated in the load resistor is, answer option C, 400 watt. Given bridge rectifier is full wave rectifier, so peak value of output voltage is 200 volt and given R equal to 50 ohm. Therefore, RMS value equal to Vm by root 2. Therefore, we will get 200 by root 2. Power dissipated in resistor equal to Vrms square divided by R. Substituting the values of Vrms and R, we get power dissipated in resistor as 400 watt. For single phase full wave bridge rectifier and 3-phase full wave bridge rectifier, the equations for various parameters. Average output voltage for single phase it is V0 equal to 2 Vm by pi. For 3-phase it is 3 Vm by pi. Average output current I0 equal to V0 by R for single phase and 3-phase. Average diode current is IDA is I0 by 2 for single phase full wave bridge rectifier and for 3-phase it is I0 by 3. RMS diode current for single phase full wave bridge rectifier is I0 by root 2. For 3-phase full wave bridge rectifier it is I0 by root 3. Average source current ISA is 0 for single phase full wave bridge rectifier and 3-phase full wave bridge rectifier. RMS source current ISR equal to I0 for single phase and ISR equal to I0 into root 2 by 3 for 3-phase full wave bridge rectifier. Question number 12. A 3-phase fully controlled converter is feeding power into a load DC load at a constant current of 150 ampere. The RMS current through each thyristor of the converter is, answer is option D, 150 by root 3 ampere. Given constant DC load current I0 equal to 150 ampere, the RMS value of the current flowing through each thyristor of converter I equal to I0 into root of 1 by 3. We get the answer 150 by root 3. Question number 13. A 500 kilovolt ampere three-phase transformer has iron loss of 300 watt and full load copper losses of 600 watt. The percentage load at which the transformer is expected to have maximum efficiency is answer option B 70.7%. Given full load kilovolt ampere equal to 500 kilovolt ampere, iron loss Wi equal to 300 watt, copper loss Wc equal to 600 watt. Maximum efficiency in a transformer occurs when copper loss and core loss are equal. Not core loss, iron loss are equal. Per unit load corresponds to maximum efficiency equal to root of Wi divided by Wcu. Substituting the values, we get it as 0.707. Therefore, percentage load corresponds to maximum efficiency 0.707 into 100, which is equal to 70.7%. Question number 40. The direction of rotation of a three-phase induction motor is clockwise when it is supplied with a three-phase sinusoidal voltage having phase sequence ABC. For counterclockwise rotation of the motor, the phase sequence of the power supply should be. Answer is option C, A, C, B. The direction of rotation of a three-phase induction motor can be reversed by interchanging any two of the three motor supply lines. Let the phase sequence of the three-phase voltage applied to the stator winding is ABC. If this sequence is changed to ACB, it is observed that direction of rotation of the field is reversed, such that the field rotates counterclockwise rather than clockwise. However, the number of poles and speed at which the magnetic field rotates remain unchanged. Thus, it is necessary only to change the phase sequence in order to change the direction of the magnetic field. Question number 15. For a tachometer, if theta of t is the rotor displacement in radians, E of t is the output voltage in volts, and K T is the tachometer constant in volt per radians per second, then the transfer function E of s divided by theta of s is. Answer is option C, Kt into S. Output equal to E of t, input equal to t. Therefore, E of t directly proportional to d theta of t divided by dt. Taking Laplace transform, E of s equal to Kt into S into theta of s. Input is not t, it is theta of t. Therefore, the transfer function E of s divided by theta of s equal to Kt into S. Question number 16. A DC potentiometer uses a slide wire of 800 mm. A standard cell of EMF 1.18 volt obtains balance at 600 mm. A test cell is seen to obtain balance at 660 mm. The EMF of the test cell is. Answer is option B, 1.30 volt. In a potentiometer, E directly proportional to L directly proportional to R, where E is the EMF of test cell, L is the balancing length of slide wire, R is the slide wire resistance. Therefore, E1 by E2 equal to L1 by L2 equal to R1 by R2. In the question they given, E1 equal to 1.18 volt, L1 equal to 600 mm, L2 equal to 660 mm. E1 by E2 equal to L1 by L2. Substituting the values of E1, L1 and L2, we get E2 is 1.30 volt. Question number 17. A 400 volt 50 kilowatt 4 pole 50 Hz Y connected induction motor has full load slip of 4%. The output torque of the machine at full load is. Answer is option C, 99.49 Newton meter. Given a number of poles P equal to 4, supply frequency F equal to 50 Hz, slip S equal to 4%, which is equal to 0.04. Output power P out equal to 50 kilowatt. Synchronous speed Ns equal to 120 F by P. Substituting the values of F and P, we get synchronous speed equal to 1500 rpm. We know slip S equal to Ns minus Nr divided by Ns. We know the value of slip and Ns. From there we can get the rotor speed Nr equal to 1440 rpm. Then the output torque of the induction motor at full load TFL equal to P out into 60 divided by 2 pi into Nr. Substituting the values of P out and Nr, we get induction output torque of an induction motor at full load TFL equal to 99.4718 Newton meter. Question number 19. An 8-pole DC generator has a simplex wave-wound armature containing 32 coils of 6 turns each. Its flux per pole is 0.06 Weber. The machine is running at 250 RPM. The induced armature voltage is answer is option C, 384 volt. Total number of conductors Z equal to coil into turn into 2. Substituting the values of coil and the number of turns into 2, we get Z equal to 384. Given flux phi equal to 0.06, speed N equal to 250, number of poles P equal to 8, number of parallel path A equal to 2 for wave wound, induced armature equal to 5 Zn by 60 into P by A. Substituting those values of Zn, P and A, the induced armature voltage we get 384 volt. The last question of this video is 20th one. A 480 megawatt 3-phase Y-connected synchronous generator has a rated voltage of 20 kilovolt at a power factor of 0.8. The line current when operating at full load rated conditions. Answer is option B, 17.3 kiloampere. Given line voltage VL equal to 20 kilovolt, power factor cos phi equal to 0.8, machine rating P equal to 480 megawatt. We know power P equal to root 3 VL IL cos phi. Therefore, from we can derive the value of line, not line voltage, line current IL by substituting the values of P, VL and cos phi. We get a line current as 17.32 kiloampere. Thank you.